Hi everyone. Today we'll continue our discussion on the analysis and design of beams for bending. Before we begin new content, let me give you the review for previous lecture. So in previous lecture, we discussed about three types of transverse loading, which resulted in like a bending of the beam. So first we considered the distributed loading, transverse distributed loading, which is distributed force. We considered point force, and we also considered a point moment. Okay, these three types of loading will induce the bending, and the difference between chapter 5 and chapter 4 is that in chapter 4 we considered pure bending case such that we only have like a non-zero m, all other reactions are zero, but now we are considering a little bit more complex case where we have both non-zero v and non-zero m. Okay, so we have to consider, when we consider the cross section, we have to consider both shear force and the moment. Then after discussing about a little bit more complex bending problems, we set our sign convention for B and M because in many cases we have to obtain the force V and moment M as a function of a position, because back in pure bending case you have exactly the same moment for entire beam, right? So you don't need to worry about which position has the largest M in chapter 4. But now we are considering a little bit more complex problem. We have to investigate which point has the largest V, which point has the largest M, and out of V and M we can obtain the normal stress and shear stress, and out of that, by comparing with material property, which is strength, shear strength and tensile strength, we have to determine whether the structure is reliable or not. And that's why we need a shear force and moment as a function of a position. Okay, and when we write down these properties as a function of position, we have to have consistent sign convention. So this is the sign convention we have when somebody asks us v as a function of s, when somebody asks us m as a function of x. We have to always rely on this consistent sign convention, especially for our lectures, our textbook, right? We may have different sign convention for different textbook, but we are now studying our textbook, and our textbook at least to say this is the sign convention. Then after discussing about three types of loading, we also discussed about three types of support, which makes the the problem like a static problem, right? Without any support, you're gonna likely have like a dynamics problem, right? So for support, we first considered cantilevered beam support. When you see this kind of diagram, this refers to rigid wall, and it mathematically represent y equals 0 and the slope dy dx equals to be 0. And simply supported support, it means that y equals 0 and m equals 0. This is the boundary condition at this point. And hinge, the boundary condition for hinge is only this, m must be 0. Right, so these are the boundary conditions you have to consider when obtaining shear force and moment as a function of position. Now we after we discussing about loadings and support, we study the relationship between shear force, moment, and distributed loading, or point moment, or point force, and we obtained three rules. In the first rule, we found that v prime, the slope of v, is same as minus qx. Here, the sign convention for load transverse force is when we have downward force, this is it is positive sign. Okay, so you gotta be careful about consistency in sign convention for transverse loading. Then when we consider m prime, the moment slope of the moment, same as v, out of this differential equation and differential relationship, we can of course obtain the integral relationship. To obtain the difference between v at x2 and v at x1, you do integration for right hand side, And it's the same for the m. When you want to obtain the difference between m at position 2 and m at position 1, you have to do integrate for the right hand side. Regarding the rule 2, when you have point external force, then delta v, the jump or discontinuity in v diagram is same as negative pe, and jump in moment is 0. And regarding rule 3, when you have point moment, external point moment, no continuity in v itself, but there is discontinuity. There is continuity in v and no discontinuity in v, and there is discontinuity in m, and the magnitude of discontinuity is minus me. Okay, so with that, we can finish the summary of the previous lecture. Okay.